heat can be transferred in three basic modes: conduction, convection, and radiation. All modes of heat transfer require a temperature difference. Conduction is the mode of energy transfer that occurs in solids, liquids, and gases. The energy is transferred from the more energetic particles of a substance to the adjacent less energetic ones. In solids, it is due to the combination of vibrations of the molecules in a lattice and the energy transport by free electrons. In gases and liquids, conduction is due to the collisions and diffusion of the molecules during their random motion. The rate of heat conduction through a medium depends on the geometry of the medium, its thickness, and the material of the medium, as well as the temperature difference across the medium. The rate of heat conduction can be determined using the rate equation based on the Fourier's law of heat conduction. Consider steady heat conduction through a large plane wall of thickness L and area A. The temperature difference across the wall is given here. Fourier's law states that the rate of heat conduction through a medium is proportional to the temperature difference across the medium and the heat transfer area, but is inversely proportional to the thickness of the medium. K is the thermal conductivity with the unit watt per meter Kelvin of the material, which measures a material's ability to conduct heat. A high value for K indicates that the material is a good heat conductor, and a low value indicates that the material is a poor heat conductor. Based on this illustration, which material do you think will burn the person's fingers first? Pure crystals and metals have the highest thermal conductivity, and gases and insulating materials are the lowest. Based on Fourier's law, for a case of delta x limit to 0, the previous equation reduces to the differential form as shown. We call this equation as Fourier's law of heat conduction. dt over dx is the temperature gradient. The heat transfers in the direction of decreasing temperature. Therefore, the dt dx becomes negative when temperature decreases with increasing x. The negative sign in the equation ensures that heat transfer in the positive x direction is a positive quantity. Please note that heat transfer area A is always normal to the direction of heat transfer. Assuming the heat conducted to the outer surface of the wall of a house in winter is convected away by the cold outdoor air while being radiated to the cold surroundings. A surface has no volume or mass and thus no energy. Therefore, a surface can be viewed as a fictitious system whose energy content remains constant during a process. Based on the given system, the energy balance is simply the rate of energy transfer in equals the rate of energy transfer out. This relation is valid for both steady and transient conditions. The surface energy balance does not involve heat generation. When the directions of interactions are not known, all energy interactions can be assumed to be towards the surface. Then, the energy balance expression is as displayed.